Hello everybody. I will take you through GOC today. So GOC is General Organic Chemistry, right? And GOC is the foundation for organic. So if you want to learn organic, you must be very thorough with GOC. You must devote sufficient time to GOC. And once GOC is over, like once you feel confident about GOC, you can start with subsequent chapters of organic. Without understanding GOC thoroughly, students will not be able to understand the subsequent chapters of organic. So when you are revising organic, ensure that you start with GOC. After GOC, you can revise the other chapters of organic. So let's start with the basic concepts, and then I will take you through a number of questions. Through questions, we'll understand the rules, the tricks to solve questions, right? Okay. First of all, see, if I draw this compound. Look at this compound, everybody. Look at this. Now, out of carbon and fluorine, fluorine is more electronegative. This is a sigma bond between carbon and fluorine. Correct? Now, if I ask you in this molecule, what kind of effect is being shown by fluorine? Is fluorine showing plus I effect or minus I effect? So I stands for inductive. Since fluorine is more electronegative than carbon, so here I will say that F shows minus I effect. Then this portion is showing plus I effect. This portion is what? CH2, CH2, CH3. Right? So, very simple. Based on the electronegativities, we have decided. Likewise, if I ask you, which effect is being shown by bromine here? Again, if you look at this bond is between carbon and bromine. So I can show the shift, or you can say the displacement of the electrons of sigma bond towards fluorine atom, right? And hence similarly here I can show the displacement towards bromine atom. Which means I will say here Br shows minus I effect. Br shows and this portion, that is C attached to 3 CH3 groups, this part, this is showing plus I effect. Right? So what is this group called? This is tert butyl group. Tert butyl. This is propyl. This is tert butyl. So I can say that whenever we have Rx, where X is a halogen, I can always safely say that R shows plus I effect and X shows minus I effect. One more point to be kept in mind is, greater the bulkiness of R, more is the plus I effect. Which means, let's say I have this. Look at this. And I have this. So X is same. Let's say that the halogen is same. Here also I'll take chlorine, and here also I'll take chlorine, or any particular halogen. So I'm keeping the halogen same in both the compounds. Now, in this compound, this group, that is R, is showing plus I effect, whereas in this one, this is R, so this is showing plus I effect. So I can say that here CH3 twice, CH2. So here this is showing plus I effect, and whereas here this is showing plus I effect. Now see, if I ask you which is having a stronger plus I effect, this group or this group, so we'll say this group shows a stronger plus I effect because here branching is more, this is more bulky. Clearly it is visible, this carbon has 3 branches coming out of it. So this group is more bulky than this group. So this group will have a stronger plus I effect. Right? Another thing is, if I compare CH3, CD3 and CT3, then this is the order of plus I effects. That means CT3 has a stronger plus I effect than CD3, CD3 has a stronger plus I effect than CH3. So as the isotope changes, the intensity of plus I effect changes. Heavier the isotope, stronger is the plus I effect in alkyl groups. So here I have changed the isotopes of hydrogen, right? All right. Now, another thing is, let's say I have this species. This is a phenyl ring, and here I have X. So again I will say here the phenyl group is showing plus I effect and this is showing minus I effect because again X is more electronegative than the carbon atom here. So phenyl ring is showing plus I, X is showing minus I. Now let's take another case. Again we have a phenyl ring here. If I ask you what effect is being shown by phenyl ring here, plus I or minus I, then what will we say? So plus I minus I will depend on the electronegativities of the groups. Now this is a carbon atom, this is also a carbon atom. This carbon atom is sp3 hybridized, this carbon atom is sp2 hybridized. sp2 carbon is more electronegative than sp3 carbon, which means in this case I will say that the phenyl ring is showing minus I effect because this carbon is more electronegative than this carbon. So the displacement of the electrons of this bond will be towards the more electronegative part, that is the ring, and CH3 here is showing plus I effect. If I compare these two cases, I can see that in this compound phenyl ring is showing plus I, right? In this compound phenyl ring is showing minus I. So it is not compulsory that a particular group will always show plus I or minus I. It will depend on what is attached to it. This is visible from these two examples. So a quick recap of inductive effect has been done. Let's go to the next effect, very important effect, that is mesomeric effect. Resonance, right? We all are required to understand resonance in detail. We draw canonical structures and then we understand plus M effect, minus M effect. So these things we do, right, in 11th standard. Quickly let's understand plus M and minus M. Now if I ask you that what is happening here, like how is the resonance structure drawn for this? How is the flow of electrons during resonance shown for this? Can I say it will be shown in this way? So if I draw the canonical structure, these are the two canonical structures of each other or resonance structures. Okay. Which means this negative charge has been pushed towards this bond and this pi bond has been pushed towards oxygen atom, where when the pi bond shifts to oxygen, the oxygen atom becomes negatively charged. Right. From this, what do we conclude? See, we can say safely that if I'm talking about this functional group, that means a ketone, COCH3 here, right? It's a ketone. So I can say that COCH3 is showing minus M effect. COCH3 is showing minus M effect. Why? Because it is pulling the electrons towards itself during resonance, which means that it is showing minus M or minus R. Minus M effect or minus R effect. Okay, another example. Let's say that I am taking a phenyl ring and to the phenyl ring NH2 is attached. So what is happening here? Again, let's look at the resonance structures. I'll not draw all resonance structures, but at least I will draw one resonance structure after this to show the flow of electrons. Here lone pair is in conjugation with pi bond, so when I start drawing the resonance structures, this is how I'll start, right? Which means the lone pair of nitrogen is being donated and this pi bond shifts. During resonance, if I ask you, electrons are moving away from NH2 or towards NH2. So we can clearly see that this lone pair is moving away from nitrogen. It's being donated by the nitrogen atom, which means I will say here NH2 is showing plus M or plus R effect. And the phenyl ring is showing minus M or minus R effect. Because the phenyl ring is accepting the electron pair from NH2. Like here, this ketone group was accepting the electron pair which was coming from negative charge. So during resonance, if a group pushes electrons away from it, it is showing plus M or plus R effect. Whereas if a group withdraws electrons or pulls electrons towards itself during resonance, it is showing a minus M effect, or so we'll say that it's a minus M causing group. Now see, if I have, let's say, this species where carbon carries a plus charge, and if I ask you what kind of mesomeric effect is being shown by NHCH3, so clearly if I start doing resonance structures, this is going to be the flow of electrons. That means again I can say that the lone pair of nitrogen is being donated. So the lone pair is in conjugation with this positive charge, which means I will say NHCH3 is showing plus M effect. Look at this. Again, here lone pair is being donated during resonance. So if I start drawing the resonance structures, these are the two resonance structures for this species. So again I can say that here this positive charge has been stabilized by the plus M effect of this oxygen atom. Here positive charge has been stabilized by plus M effect of NHCH3. So remember that whenever the lone pair of any atom is in conjugation with positive charge of carbon, stability increases, and we say that the carbocation has been stabilized by plus M effect. Both these examples show that. More the plus M effect, more is the stability of carbocation. This is a carbocation, this is also a carbocation because carbon carries plus charge. And if there is no plus M effect, like we have this case, if you look at this carbocation, there is no plus M effect at all because there is no such group which can participate in resonance here. There is no resonance at all. There is no conjugation here. So here I will start counting alpha hydrogens to comment on stability. This is alpha carbon, this is alpha carbon, this is alpha carbon, because positively charged carbon is this one, right? So these are the three alpha carbon atoms. Alpha hydrogen atoms are those hydrogen atoms which are directly bonded to alpha carbon atoms. So 3 here, and 2. 3 plus 3 plus 2, 8. So I will say this as 8 alpha hydrogen atoms. And let's say if I'm comparing the stability of this carbocation with the stability of this carbocation, then I will say that the carbocation which has more alpha hydrogens is more stable. See, in both of these there is no plus M effect. Since there is no plus M effect, I will start counting alpha hydrogens, and then I will come to a conclusion that more the number of alpha hydrogens, more is the stability of carbocation. So here there are 2 plus 2 plus 2, 6 alpha hydrogens. So this is more stable than this because this has more alpha hydrogens than this. Now, if I compare this and this, or this and this, then definitely this is much more stable because here we have plus M effect. So more the plus M effect, more is the stability of carbocation. If there is no plus M effect, we start counting alpha hydrogens, and then we say more the number of alpha hydrogens, more is the stability of the carbocation. Carbocations are extremely important. We come across carbocations in so many chapters, right? Hydrocarbons, alcohols, phenols, ethers, right? Okay. Carbanions. Let's say I have this carbanion, and also I have this carbanion. Okay. Now, clearly we can see that this group is showing minus M. Similarly, here we can say that this group is showing minus M. Likewise, here also, this group is showing minus M and this group is showing minus M. So in both the carbanions, let's label them. So in both the carbanions, we have minus M causing groups. More the stability, more the minus M effect, more is the stability of the carbanion. So which is more stable, A or B? So we will say that that carbanion where minus M effect is stronger is going to be more stable. So minus M is stronger in case of B. So I will say B is more stable than A. Now why is that so? Why did I say that in B there is more minus M? See, in A you have a ketone this side and you have a ketone this side, which means there are two ketones. Here you have two aldehydes. You must remember that the minus M effect of an aldehyde is stronger than the minus M effect of a ketone. The minus M effect of a ketone is stronger than the minus M effect of an ester. So, since we have two aldehydes here, minus M effect is stronger here, and so B is more stable than A. What if I have this carbanion and this carbanion? Let's label them. Both of these are carbanions. Which is more stable, P or Q? Now, here again we have minus M effect shown by NO2. Here we have minus M effect shown by CHO. CHO is aldehyde, NO2 is nitro group. You always need to remember that the minus M effect of NO2 is very, very strong. That means NO2 is the group which has the highest intensity of minus M, which means minus M effect is very high here because of NO2, and hence we can say that P is more stable than Q. So minus M effect of NO2 is very, very strong. So minus M effect or minus R effect of NO2 is stronger than minus M effect of CN. Minus M effect of CN is stronger than minus M effect of aldehyde. Minus M effect of aldehyde is stronger than minus M effect of ketone, and minus M effect of ketone is stronger than minus M effect of ester. This is the sequence which will help you again and again in multiple problems. Right? Similarly for plus M, if we discuss, then I'll quickly tell you the most common groups which we encounter again and again. So the plus M effect of O minus is stronger than the plus M effect of NH2. The plus M effect of NH2 is stronger than the plus M effect of NHR. The plus M effect of NHR is stronger than the plus M effect of NR2. The plus M effect of NR2 is stronger than the plus M effect of OH, and the plus M effect of OH is stronger than plus M effect of OR. So you should remember this. So more the stability, more the plus M effect in a carbocation, more is the stability of the carbocation, and more the minus M effect in a carbanion, more is the stability of the carbanion. Okay. So let's proceed now. We will discuss some questions. Okay, first question. Consider the following statements. Okay, so this question is based on carbocations. See, carbon carries a plus charge. As I said, carbocations are very common. We come across carbocations so many times. Okay, now these are the options. Which statements are correct? Okay, first statement. Yes, first statement is correct because we have lone pair of oxygen which is able to stabilize the plus charge because this OCH3 is showing plus M effect. Okay, here there is no plus M effect, so A is a correct statement. Next one, This is more stable than this. Let's see. Now what is Me2CH plus? Me2CH plus is this. This has 6 alpha hydrogens, right? These are the 2 alpha carbons, so we have 6 alpha hydrogens. Here this is the alpha carbon, there are 2 alpha hydrogens. There is no plus M, so we'll say that more the number of alpha hydrogens, more is the stability of the carbocation. So yes, B is also a correct statement. Next one, C. Okay, C is interesting. See, here pi bond is in resonance with positive charge. That means I can say that because of resonance, this will be more stable because the pi bond is being donated towards the positively charged atom. That means here also we have basically plus M effect shown by the pi bond, because what is plus M effect? During resonance, if pi electrons are moving towards plus charge, then we'll say that yes, the carbocation is being stabilized by plus M effect. So yes, we can say this is more stable than this. Here there is no plus M effect at all. So this is a correct statement. Next one. Now this is a wrong statement, because if you notice carefully, the hybridization of this carbon will be sp. Positively charged carbon is placed on this carbon and there's a double bond. So this has to be, this is vinyl cation, right? Vinyl cation is not formed, it is highly unstable. This is ethyl cation. So I can say that here this is less stable. In fact, this is highly unstable because the hybridization of this carbon atom is sp, vinyl cation. So in short, remember that such carbocations are highly unstable. They are not formed because whenever you have this system, we will say straight away this is highly unstable. Okay, fine. So A, B and C are correct statements. This is highly unstable, so never form this. Which of the following carbon atoms has most acidic hydrogen? Okay, this concept is very important. Now what is this concept? What is this concept? So acidic hydrogen is being talked about. If something has an acidic hydrogen, it will be able to lose H plus. That means it will be able to donate a proton. That means it's acting as an acid. So for example, if I'm saying that AH is having an acidic hydrogen and that is this one, that means this H plus will, this H will go out in the form of H plus. This is what I'll get, because when the bond shifts towards A, H goes out as H plus. Now if this process happens easily, that means this substance is acting as a good acid. So if AH is containing one acidic hydrogen and that is this H, then I can say that this process happens easily. Which means, in other words, if after taking out a proton, because H plus is a proton, right? So if I take out a proton and after that if I am able to obtain a very stable species, that means that proton can be lost easily, and so I will say yes, that hydrogen is acidic in nature. Okay, so which of the following carbon atoms has the most acidic hydrogen? That means if I take out one hydrogen atom in the form of a proton and then compare the stability, I will be able to conclude. Let's take out hydrogen atom from this carbon which has been labeled 2. So what will happen if I do that? I will get this species. And we can say that yes, negative charge is being stabilized by resonance. But if I take out one hydrogen atom from this carbon, then negative charge appears here and this negative charge is not being stabilized by minus M effect. See, here the negative charge has been stabilized by minus M effect of this aldehyde. But here if negative charge appears, that will not be stabilized by minus M effect because there is no resonance between this negative charge and any other group. Similarly, if I take out hydrogen atom from this carbon, I'll get negative charge on this carbon, and then this negative charge again is not being stabilized by minus M effect, which means this is the most acidic hydrogen. Okay, what about 1? See, this hydrogen is a part of CHO, that cannot be taken out. So this is out of question. This is aldehyde, right? You cannot remove the H of CHO. So the most acidic hydrogen is here. The carbon which has been labeled 2 contains the most acidic hydrogen. So C2H, that means this one. Why? The proof is here. The negative charge is being stabilized by minus M effect of aldehyde. So I'll say that the aldehyde is showing minus M effect here. So whenever we are interested in finding out the most acidic hydrogen, we have to follow this step. We have to remove a proton and then see how negative charge is being stabilized. Greater the stability of negative charge obtained after removal of a proton, higher is the acidic strength of that particular hydrogen. That means greater is the ease of deprotonation, because that hydrogen atom will be lost easily, and after it has been removed we will get a stable species because the negative charge is being stabilized. So always check how the negative charge is being stabilized. Again you see similar question, most acidic hydrogen or most acidic proton. Take out one hydrogen atom and check. So in option A I will get this species if I take out hydrogen from this carbon. In option B I will get this species if I take out hydrogen from this carbon. In option C I will get this species if I take out this hydrogen atom, that is one hydrogen from this carbon. And here I will get this. Okay, very simple now. Okay, so check. Here the negative charge is being stabilized by minus M effect of this ketone. Here the negative charge is being stabilized by minus M effect of this aldehyde. Here negative charge is being stabilized by minus M effect of 2 ketones. And here the negative charge is being stabilized by minus M effect of 3 ketones. That means there are 3 minus M causing groups which are stabilizing this negative charge. So negative charge will be extremely stable because there are 3 minus M causing groups here, which means D contains this hydrogen atom which is acidic, and out of A, B, C, D, D has the most acidic hydrogen, because once D loses this hydrogen we will get this conjugate base, and here in this conjugate base the negative charge which is appearing on carbon is being stabilized very nicely by 3 minus M causing groups, which is not an aromatic compound. Alright, now one very easy technique is to check the hybridization of every atom of the ring. I mean, this is the first step which you should follow when such a question appears. Any question based on aromaticity, non-aromaticity, anti-aromaticity should be tackled in this way. The first step is to check the hybridization of every atom of the ring. If you look at this compound, this carbon atom is sp3 hybridized. If one atom of the ring is sp3 hybridized, that means that ring is not planar. And if the ring is not planar, it cannot be aromatic. So it is not aromatic. And what is the category to which it belongs? It is non-aromatic. I repeat, if there is one atom which is sp3 hybridized, I mean the atom which is a part of the ring is sp3 hybridized, immediately we'll say it is the non-aromatic species. And if there are 2 or more than 2 atoms which are sp3 hybridized, then also we will say that it is a non-aromatic ring. See, I did not check the hybridization of this atom, although this is sp3. Why? Because even if one atom of the ring is sp3 hybridized, the species is going to be non-aromatic. So I don't have to check every atom of the ring if one atom is sp3. But yes, if every atom of the ring is sp2 hybridized, then you will check whether the species is aromatic or anti-aromatic. But even if only one atom of the ring is sp3, immediately we can conclude that the ring is non-aromatic because planarity is not achieved, and hence we'll say it's non-aromatic. So this is aromatic, this is aromatic, this is aromatic. See, every atom is sp2 hybridized here. Every atom is sp2 hybridized. Every atom is sp2 hybridized. And after we are sure that every atom is sp2 hybridized, we will start checking this concept, 4n plus 2 and 4n. How many electrons inside the ring are in conjugation? How many electrons are in resonance? That is the number of pi electrons in resonance, right? The total number of pi electrons in conjugation inside the ring. And then we find out the value of n, and then if we say, see that the value of n from this equation is 0 or 1 or 2, then we'll conclude that the species is aromatic. And here from this, if the value of n is a positive integer, we'll say that the species is anti-aromatic. But when? After the ring is planar. But here the ring is not planar. So immediately I said that the ring is non-aromatic. Next one. The correct order of decreasing basic strengths is, okay, a very good question. Now, basic strength. Remember, if nitrogen atom is acting as a donor, donor means the atom which is eager to donate its lone pair or the electron pair. Now, what is a base? A base, if a base is negatively charged, then this negative charge is donated to H plus. I will say now B minus is functioning as a base because it is giving its electron pair to H plus. But if it is neutral, then also I can call it a base if it has a lone pair. And now also I will say that this neutral B is a base because again here the lone pair is being given to H plus, which means a base is a substance which donates electron pair to H plus. Donates electron pair to H plus means it is accepting a proton because it is accepting H plus. Now, if nitrogen is acting as the donor and we see that the lone pair of nitrogen atom is involved in resonance within the molecule, that means if it is very nicely or effectively delocalized within the species, then the basic strength of the entire species is very low because the lone pair is busy in resonance within the molecule. It will not be easily donated to H plus. This is the concept. So I repeat, whenever the lone pair of nitrogen atom is involved in resonance significantly, that means to a very great extent, then the basic strength of the entire species falls. But if lone pair of nitrogen is not at all involved in resonance, then the basic strength is going to be high. Okay, that is the first thing. So let's see these four species. All these are bases, right? All these are bases, and every base has a nitrogen atom which is acting as a donor. Now see, these all are neutral. These all are neutral. Okay, let's look at the fourth one. This is aniline, very common, right, in organic. Clearly it is visible that the lone pair of nitrogen in aniline is involved in resonance. This is pyrrole. In pyrrole again, if you see, the lone pair of nitrogen is involved in resonance. Okay. Here the lone pair of nitrogen is not involved in resonance at all. Here also the lone pair of nitrogen is not involved in resonance. Never make this mistake. This is pyridine. In pyridine, the lone pair of nitrogen is never a part of conjugation. So not involved in resonance. I'll write here. Not involved in resonance. So one thing is very clear, 2 and 3 are going to be more basic than 1 and 4. Because in 2 and 3 the lone pair of nitrogen is not involved in resonance. Okay. Now how to compare 1 and 4? In 1, the lone pair is involved in aromaticity. See, I was talking about 4n plus 2 rule. So 4n plus 2 is equal to 6 in case of 1. Now how did I get 6? See, this pi bond is in conjugation with this lone pair, and also this lone pair is in conjugation with this pi bond, and this pi bond is again in conjugation with this pi bond. So I will say 2 electrons of lone pair, 2 electrons of this pi bond, and 2 electrons of this pi bond are in conjugation with each other. 2, 2, 2, 6. And from here n is equal to 1. So if n is equal to 0 or 1 or 2 or 3, then the ring is aromatic. This is aromatic, and I get 6 when I include the lone pair also. So we can conclude that in pyrrole, the lone pair of nitrogen is involved in maintaining the aromaticity, because when I count this, then only I get 6. See, this lone pair is in conjugation with this pi bond is in conjugation with this pi bond. So 2 electrons of lone pair are in conjugation with 2 electrons of pi bond, and again these 2 electrons of pi bond are in conjugation with these 2 electrons of the lone pair. So in total there are 6 electrons in resonance within the ring. Now look at the fourth one. See, now if you look at the fourth one, if I don't look at NH2, then also this ring will be aromatic because of this system of 3 pi bonds. The pi bonds are in resonance. So even if I don't look at this part, still this ring will be aromatic because of the 3 pi bonds which are in conjugation. Which means this is aromatic because the lone pair is in conjugation with the pi bonds. This ring is aromatic even if the lone pair of nitrogen is not a part of it. That means if there is no NH2, then also this ring will be aromatic. So the involvement of this lone pair in resonance is more than the involvement of this lone pair in resonance, because in case of this compound, that is in case of pyrrole, the lone pair is involved in maintaining aromaticity. Hence 1 is less basic than 4. So this is clear. 1 is less basic than 4. Okay. Now 2 and 3. This nitrogen is sp3. This nitrogen is sp2. sp3 nitrogen is always more basic than sp2 nitrogen. So 2 is more basic than 3. Now combine these two results. So 2 is more basic than 3, and we have discussed that already. We have discussed one thing, that 2 and 3 are more basic than 1 and 4. So 2, 3, 4, 1. This is going to be the correct order. 2, 3, 4, 1. 2 is the most basic compound, followed by 3. Out of 1 and 4, 4 is more basic because 1 is highly aromatic. 1 is aromatic because in 1 the lone pair of nitrogen is involved in maintaining resonance. So the lone pair of nitrogen is a part of aromaticity, that is Huckel's rule, 4n plus 2 equal to 6. And so it is very much busy within the ring in maintaining the aromaticity, and hence it will not be donated very easily. So pyrrole is the weakest of all. Weakest means 1 is at the end. So option D is correct. You should remember that this is called pyrrole, and this is called pyridine, and this is called aniline. Which of the following acid-base reaction is not feasible? Okay. See, whenever they write H plus on top of the arrow, that means you are reacting this species with an acid. H plus is coming from an acid. So acid-base reaction is happening. We know that if there are multiple donor atoms within a species, then the one which is most basic will undergo protonation the most easily. This is protonation because the reaction with H plus is called protonation. So the donor atom which is the most basic, that means the one which has the highest tendency to donate its electron pair, is going to undergo protonation very easily, and so H plus is going to get attached to that nitrogen which is the most basic. Let's see now. In A, these are the 2 nitrogen atoms. Okay. Now if you notice carefully, again that same old concept is back. Here this lone pair is involved in resonance. which means this nitrogen is more basic than this nitrogen, because the lone pair of this nitrogen atom is not involved in resonance, whereas the lone pair of this nitrogen atom is involved in resonance. So this is more basic. So this should undergo protonation if I take one equivalent of H plus, whereas in this it has been shown that this nitrogen is undergoing protonation. So this is incorrect. Incorrect means not feasible. That's what they have asked, which is not feasible. One more thing, this compound is very important. It's called guanidine. You should remember its name. Guanidine is a highly basic compound. It's very basic, okay? And this acts as the donor. So guanidine is a very highly basic compound, and you should know the donor within guanidine. So this nitrogen atom is the donor. Very, very important. Okay. Now coming to guanidine ones, see. Also, if you look at this nitrogen atom again, so I will get two canonical structures wherein this nitrogen atom will be negatively charged, and hence this is the donor. More the accumulation of negative charge on a nitrogen atom because of resonance, greater is its ability to donate electron pair, which means this is the donor, this is the best site of protonation. So this is undergoing reaction with H plus. These two nitrogen atoms are not so basic because their lone pairs are involved in resonance. Select the correct option for order of stabilities of canonical structures. Alright, for order of stabilities of canonical structures, the first thing to check is how many atoms have complete octet. Let's see. How many atoms have complete octet? Okay. In X, this has an incomplete octet because any positively charged carbon will have an incomplete octet. In Y, every atom has a complete octet. Okay. In Z, this carbon atom has an incomplete octet because again this is positively charged, which means Y is the most stable canonical structure because in Y, every atom has a complete octet. So Y is the most stable canonical structure. Okay, next is to see the appearance of negative charge. That means which atom is carrying the negative charge. If you look at X, O is carrying negative charge. If you look at Z, carbon is carrying negative charge. Remember, negative charge is more stable on oxygen than on carbon because oxygen is more electronegative than carbon. So I will say that X is a more stable canonical structure than Z. So Y is the most stable one, then X, and the least stable one is Z. So Y, X, Z. The order of CC single bond lengths would be. Alright, now here we have resonance. Due to resonance, here we have double bond character. Here, if you see, there are 3 alpha hydrogens. If I look at B, these are the 3 alpha hydrogens. If I show CH3 in this manner, then it will be easier for you to figure out. Now, because of these 3 alpha hydrogens, hyperconjugation will take place, and due to hyperconjugation, again here we will have double bond character. But resonance is more powerful than hyperconjugation, so the impact on bond length due to resonance will be higher than the impact on bond length due to hyperconjugation, which means here the double bond character is more than the double bond character here. More the double bond character, shorter is the bond length. So in A, this bond length is going to be the shortest, right? In A, this bond length is going to be the shortest. So this is correct because in C you have a pure single bond. This is a pure single bond. Pure single bond means there is no double bond character at all. There is no hyperconjugation. There is no resonance, and so this remains a pure single bond. And a pure single bond is the longest. So more the double bond character, shorter is the bond length. Next, cyclopentadiene. This is called cyclopentadiene. Hydrogen atom attached to sp3 carbon. This is the sp3 carbon atom, right? Can be removed easily as. Now see, if I talk about this particular hydrogen atom, if I remove proton, that means H plus, I will get this species. This species is aromatic. This species is aromatic. Why? Again 4n plus 2 is equal to 6 here. How 6? Negative charge means 2 electrons. These 2 electrons are in resonance with this pi bond, and then also these 2 electrons are in resonance with this pi bond, and this pi bond is in resonance with this pi bond. So overall 6 pi electrons are in resonance, and from here n is 1. Species is aromatic. We know aromatic structures are highly stable, which means that if this gives a proton, it gets converted to an aromatic species, and that is stable, and so it can easily give its proton. So the hydrogen atom goes out in the form of a proton, because after it goes out, we get a very stable species. Which one is more stable? Free radical. Free radical, okay. Again, for comparing the stabilities of free radicals, we check plus M, and then we check alpha hydrogens. Alpha hydrogens means plus H, that is hyperconjugation. So here if you see this dot, that is this radical, is in resonance with the pi bond here. Okay, here also you can see that resonance is happening. Here in this way resonance is happening. Here there is no resonance. Here also there is no resonance. So forget these two. So I can say that here there is plus M effect, that is the pi bond shifts towards the radical. Here also that there is plus M effect because pi bond shifts towards the radical. But additionally here we can see that there are alpha hydrogens as well. Me means CH3. So this carbon is carrying the dot. These are the alpha carbon atoms. So 3 plus 2, 5 alpha hydrogens are present. Here there is no alpha hydrogen, so A is more stable than C. Because in A, plus M is also operating, plus H is also operating. Plus H means the hyperconjugation happening due to the alpha hydrogens. Which is wrong electromagnetic effect. Wrong, okay. Now see, in electromagnetic effect, the pi bond shifts towards more electronegative atom. This is wrong because nitrogen is more electronegative than carbon. So this is how the shifting should have been shown. This is the correct electromagnetic effect. So this is wrong. They have asked which is wrong, so C is wrong. This is the correct one. Here negative charge is appearing on carbon, whereas negative charge should appear on nitrogen. Tautomerism is exhibited by. Now for tautomerism, see the aldehyde or ketone. So here we have a ketone, this is alpha carbon, this is alpha carbon. Here again ketone, this is alpha carbon, this is alpha carbon, this is again a ketone, alpha carbon, alpha carbon. This is an aldehyde, this is an alpha carbon. Now, if there is at least one alpha hydrogen atom, if there is at least one alpha hydrogen atom such that the alpha carbon to which that hydrogen atom is sp3 hybridized, then we will say that yes, tautomerism is possible. So let's check here. This alpha carbon is sp3, but there is no hydrogen atom attached to it. This alpha carbon is sp3, but there is no hydrogen atom attached to it. So tautomerism is not possible here. Again here, this alpha carbon has a hydrogen, but this is sp2. So we cannot say that tautomerism is possible. Why? Because had this been sp3, then I would have said that yes, there is hydrogen atom attached to alpha carbon, and alpha carbon is sp3, so tautomerism is possible. But now I cannot say that tautomerism is possible because here this carbon, which is alpha with respect to this ketone, is sp2 hybridized. Same issue with this and with this as well, because with respect to this ketone, this is alpha, and here also the same problem is happening. So here tautomerism is not possible. Let's come to D. This carbon is alpha carbon. There is no hydrogen atom attached to this alpha carbon. Also this is sp2. So even if there were, we would say tautomerism is not possible, because if alpha is sp2, if the alpha carbon atom is sp2, then the hydrogen atom attached to that alpha carbon is not considered enolizable, because it does not it is not an enolizable hydrogen atom, so it should not be taken into consideration. So here we did not take into consideration the hydrogen atom attached, because this is sp2. Here also same problem, hence we are left with this. So this is the alpha carbon with respect to NO2, and from here tautomerism is possible. So like this we can show tautomerism here. Right? So one H will go here. So I'll show it here. Okay. So this is the tautomer of this. So these two are tautomers of each other. Now see, this alpha carbon is sp3, and also it has hydrogen atom attached to it. Next, again similar question. Identify the compound which exhibits tautomerism. Methanol is HCHO. This cannot show tautomerism because there is no alpha carbon. This is phenol. Butene. This is butene, and this is lactic acid. This cannot show. There is no aldehyde, there is no ketone, there is no such functional group. Okay, this also cannot show. So only this can show. Only this can show, phenol. Okay. So in this way phenol will be formed. Okay. So this is sp3. It has two enolizable hydrogen atoms. This is sp3 carbon. So this is the keto form. This is the enol form. This is how we can say that these two are tautomers of each other. So this can undergo enolization, and this is the keto form of this. So we can say that tautomerism is possible because these two are the tautomers of each other. Acidic strength. Same logic. Take out one hydrogen atom and form negative charge. So here I'll get CH2 minus NO2. Here CH minus NO2. Here this, and here this. Negative charge will be stabilized by 3 minus M causing groups. So fourth is the most acidic compound, followed by 2 in 2 minus charge is stabilized by 2 minus M causing groups, and then we have 1, and then we have 3. This will cause a problem because CH3 has sp3 carbon. Hence, I'll say that 3 is less acidic than 1. So 4, 2, 1, 3. A option. Four, 2, 1, 3. See, this negative charge is stabilized by minus M of NO2. Here also negative charge is stabilized by minus M of NO2. But why is 1 more acidic than 3? Because in 3 you have this additional group R. R attached to a negatively charged carbon decreases stability of negative charge. Radical. So most stable radical will be this one because we have resonance between pi bond and radical. So 2 is the most stable free radical. Least stable will be 4 because this has 0 alpha hydrogen. No alpha hydrogen, no resonance. Right? This will be more stable than 3 because there are 2 alpha hydrogens here, whereas here we have 9 alpha hydrogens. So 2, 1, 3, and then 4. Next one. Which is the strongest acid? So which is the strongest acid? Now see, Carbolic acid is phenol. Carbonic acid is H2CO3. Acetic acid is CH3COOH. And picric acid is 2,4,6-trinitrophenol. Remember one exception. Picric acid is more acidic than carboxylic acids. Hence, C is the strongest acid. Had this not been there, we would have said a carboxylic acid is stronger than phenol, it is stronger than alcohol. But only when it is picric acid, we'll say picric acid is more acidic than carboxylic acids also. This is picric acid, so C is the answer. Next one. See, NaNH2 is a very strong base. If 1 mole of the base has been used, then in this compound the most acidic hydrogen will react, because we have only 1 mole of the base. Which is the most acidic hydrogen in this molecule? We have phenolic group, we have alcohol, we have sp, hybridized carbon containing 1 hydrogen atom, and here we have COH. Obviously COH is a stronger acid than phenol, COH is a stronger acid than alcohol, and COH is always a stronger acid than this hydrogen attached to sp carbon. Hence answer will be obtained if I take out 1 H plus from COOH. So this base will abstract proton from COOH selectively and not from the others, because this is the group which is the strongest acid out of all of these. Hence answer will be D. COONA means COO minus Na plus. Negative charge has appeared on oxygen because H plus has been taken by NH2 minus coming from NaNH2. So this NH2 minus grabs a proton because NH2 minus is a strong base. The correct order of acidic strengths is, alright, a carboxylic acid is stronger than alcohol. Okay, we all know that water is a stronger acid than alcohol. And also we know that any carboxylic acid is a stronger acid than water. Out of HCN and CH3COOH, out of carboxylic acid and HCN, carboxylic acid is a stronger acid. So this is the correct answer. Okay, similar logic. Again, carboxylic acid is the strongest. Okay. Water is a stronger acid than alcohol, just now we discussed. Now, if you look at this species, if I take out 1 proton from HC triple bond CH, I'll get this species. If I take out 1 proton from water, I'll get OH minus. Which is more stable? Obviously, this is more stable because here negative charge is appearing on oxygen. Here negative charge is appearing on carbon, which means H2O is more acidic than HC triple bond CH. So, which is the answer? B. And obviously, if I take out 1 H plus from ROH, I'll get RO minus. Again, this is more stable than this because again, using the same logic, we will get that RO minus is more stable than this because here negative charge is appearing on oxygen. Here negative charge is appearing on carbon. See, whatever the species is, irrespective of what we have, R, H, whatever, negative charge on oxygen is always going to be more stable than negative charge on carbon. So, ROH, RCOOH, H2O, all of these are more acidic than HC triple bond CH. So, this will be at the end. So, B is the answer. Okay, again similar logic. This is a base, negatively charged species is a base will take out a proton, and we will realize that C is the answer because C has this hydrogen which is acidic. Once a base, that is CH3, CH2O minus in this case, takes out the proton, we will be getting an aromatic species. So very, very desired phenomenon. Right? How many of the following compounds are more basic than aniline? Very interesting question. Remember, this is aniline we have already discussed, and the point is, if any group is attached at ortho position of NH2, this is always going to be a weaker base than aniline. always, irrespective of what G is. Irrespective of what G is, right? So G can be halogen, G can be methyl, ethyl, propyl, G can be plus H, plus I, minus M, NO2, anything. So this species is always less basic than aniline. They have asked how many of the following compounds are more basic than aniline. So this is definitely not, because it comes under this category. This is more basic than aniline because CH3 will show plus I. Why plus I? Because CH3 is attached at meta position of NH2. When you see that a group is attached at meta position of NH2, you just consider inductive effect. You don't consider plus H, you don't consider plus M, you don't consider minus M, because at meta only inductive effect operates. Your reference is this, right? Okay. Fine. Here also, if you see, the nitrogen atom is sp2 hybridized. Now here there is no resonance, whereas in aniline resonance happens because the lone pair of nitrogen in aniline is in resonance with the pi bond of the ring, which means because there is no resonance here, this is more basic than aniline. This already we know, Nr2 attached to phenyl ring is more basic than aniline. This will be less basic because NO2 will show minus I. This will be more basic because this will show plus M. So yes, this is more basic than aniline. At para we consider mesomeric effect. This is at para with respect to NH2, right? Again, NHR similar to this. So Nr2 and NHR are always more basic than NH2 attached to the ring. So even this one. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. More basic than aniline. How many of the following compounds give CO2 on reaction with NHCO3? Very, very interesting and important as well. This is called squaric acid. You have to remember that squaric acid is highly acidic. Squaric acid reacts with NaHCO3. HCl, HBr, HI, H2SO4, HNO3, HClO4, all these react with NaHCO3. All sulfonic acids react with NaHCO3. Okay. All carboxylic acids react with NaHCO3. Now, alcohol, C2H5OH is alcohol. Any alcohol does not react with NaHCO3. This will not be able to react because this is a base, right? So it will not react. Now, coming to derivatives of phenol. Here you have phenolic group, here also you have phenolic group. Remember, phenol then orthonitrophenol, metanitrophenol. These do not react with NaHCO3, so they will not produce CO2 gas. Whereas paranitrophenol reacts with NaHCO3 to form CO2 gas. Picric acid is highly acidic, so it reacts with NaHCO3 to form CO2 gas. So how many of the compounds are giving CO2 here? 1, 2, 3, 4, 5, 6. So all carboxylic acids will react with NaHCO3 to form CO2 gas. All sulfonic acids will react with NaHCO3 to form CO2 gas. Squaric acid will react, right? And picric acid and paranitrophenol and 2,4 dinitrophenol also reacts with NaHCO3. So 1, 2, 3, 4, 5, 6. So option C. Next one. How many are more acidic than HCOH? Remember, if you have a minus I causing group attached to this carbon, then this entire compound is more acidic than HCOH. So going by that logic, this is more acidic than HCOH, this is more acidic, this is more acidic, this is more acidic because Cn is minus I, F is minus I, NO2 is minus I, Cl is minus I, this is minus I. This is NH minus, so this will be showing plus I because already there is negative charge on an atom. So don't go wrong here, right? Here this is showing minus I because there is a positive charge here, NH3 plus, right? So how many of the compounds are more acidic than HCOH? 1, 2, 3, 4, 5. Less pK than benzoic acid. Less pK than benzoic acid means more acidic than benzoic acid. HCOH is more acidic than benzoic acid. This is not. So remember, RCOH is less acidic than benzoic acid, but HCOH is more acidic than benzoic acid. Again, this is not, because OH will show plus M, and plus M decreases acidic strength. This is highly acidic. Now remember, whenever you have COOH and a group attached at ortho of it, this entire thing is always more acidic than benzoic acid, irrespective of what G is. So this is more acidic than normal benzoic acid. Again, going by that same logic, G is CH3, but irrespective of what G is, the entire compound is more acidic because you have a group attached at ortho of COH. This is more acidic because halogen is there. Halogen shows minus I. Now this will be less acidic because of plus M decreases acidic strength. This is more acidic than benzoic acid because again minus I of NH2 will be considered. NH2 is at meta, and so minus I will be considered. So how many are more acidic than benzoic acid? 1, 2, 3, 4, 5. Okay. Easy question, you have to write down the reaction. Acetic acid is CH3COH reacting with NaHCO3. We know that a carboxylic acid reacts with sodium bicarbonate to form salt. So the salt will be CH3COONA. So I'll write down the products here. CH3COONA. Carbon dioxide gas will be evolved if any carboxylic acid reacts with NaHCO3, and definitely we'll have water as well. Let's check whether this equation is balanced or not. Okay, so CH3COONA, and yes, so it's balanced. So let's apply mole concept. Already they have mentioned that excess of NaHCO3 has been used, which means this is the limiting reagent. And we know that all calculations of stoichiometry are based on limiting reagent. 90 grams of acetic acid. So how many moles of acetic acid reacted? 90 upon 60, because 60 is the molar mass. So this is the moles of acetic acid reacted. 1.5 moles. 3 by 2 is 1.5. 1.5 moles of acetic acid are reacting. So how many moles of CO2 gas will be evolved? 1 mole. 1.5 moles, because the ratio is 1:1. So if 1 mole of this reacts, 1 mole of CO2 is formed. If 1.5 moles of this react, 1.5 moles of CO2 are formed. So 1.5 moles of CO2 have been formed. Now see, what is the volume at STP? We know that at STP the volume is what? It is the number of moles multiplied by 22.4. The volume in liters at STP is number of moles multiplied by 22.4. On solving this, what do we get? We get 33.6 liters. 1.5 is 3 by 2 if you show this calculation, right? And then we'll say that we are getting this. 11.2 into 3 is 33.6 liters. 33.6 liters. So B is the answer. So without the reaction you will not be able to proceed. Okay. So I hope we have covered most of the concepts. So keep revising GOC, and it is going to be extremely